Is a trick to do a problem like this so much faster than what this is. We do teach you this just foundationally so you understand when we move on, but there is a trick to do implicit differentiation a lot faster, and it's probably, I think, a little bit easier too. Welcome to Cranky Calculus, and we have implicit differentiation. Please like and subscribe for more content like this. So implicit differentiation is a type of differentiation where we have y values, not just as y equals, but y values on both sides of the equation, or we're doing some stuff to the y's, such as multiplying y's, adding y's, squaring y's, whatever. So examples of that are going to be right down here for implicit differentiation. Is you can see the explicit y equals x squared, but the implicit version that would be x equals y squared. You can kind of see what happens here for each of these. The explicit, you should be familiar with how the explicit works. We have dy dx equals 2x. Technically, we have a dx over dx because we're differentiating x with respect to x. That just equals 1. That goes away. When we do this implicitly, we have to tag the y using chain rule with the dy dx. So what does that look like? Well, we do have some procedures here to do implicit differentiation. So you're going to differentiate both sides of the equation with respect to x. Use chain rule to differentiate y, so that is, I call it tagging dy dx. We're going to collect all of our dy dx's on the one side of the equation, finally put all the other terms on the other side, and solve for dy dx. So for our first example here, it will kind of draw out exactly what we're doing. We're going to find the equation of a tangent line to the circle at x squared plus y squared equals 25. So if I were to have an axis right here, and here is my circle, the radius of 5, and we're going to go to the point -3, 4, which is about there-ish. I want to find the equation of this dashed blue line. That's the whole point of that. So what I need to do is need to do y minus y1 equals the slope x minus x1. Okay, and this -3 right here is going to be my x1. That 4 is my y1. So to find the slope, I need to differentiate both sides. So to differentiate all the way through this equation, the derivative of x squared is going to be 2x. Plus, the derivative of y squared is 2y. Now, since we're differentiating with respect to x, this is going to be dy over dx equals, a lot of people make mistakes on this one. The derivative of 25 is just going to come out as 0. I see lots of errors from students that will accidentally put 25 there just because they're not thinking. They're not going slow enough. They're rushing. Okay, once we're here, we can find dy dx and solve by subtracting 2x on both sides. So we're going to end up with 2y dy dx equals -2x. This is me collecting my dy dx's. I just have one, so it's not a big deal. Divide both sides by this 2y. And we're going to end up with dy over dx is equal to -x over y. Now, I'm going to use this to find my slope of my tangent line. So the slope is going to be equal to my dy over dx at the point -3, 4. So this is notation that's acceptable. And what we're going to do is plug in a -3 and a 4, which is going to end up with being a -3 all over 4. So my slope is 3/4. So now I'm going to take everything that I have and plug it into this lovely tangent line equation. So I'm going to get y minus y1, which is 4, equals 3/4. And this is going to be x plus 3. And that's going to be my final answer here for this problem, which makes sense. Sometimes you got to make sense of these problems, and you can see that that tangent line right on over here has a positive slope. So saying that this is m equals 3/4 is totally fair, and that is our tangent line for that. Next up here on our implicit differentiation notes is we're going to solve for dy dx in terms of x and y, and we have, this is a big one here, cosine of x plus y equals x squared e to the y. So on the first example we did, all the terms were isolated pretty nicely. On this one, it's going to be a bit more of a bear because we do have chain rule here and we do have product rule. So let's go through on the left-hand side. To differentiate cosine x plus y, we're going to differentiate the outside first. So it's going to turn into negative sine x plus y, and then now we need to differentiate the inside. So the derivative of the inside is 1 plus dy over dx. So that was our chain rule on that left-hand side. On the right-hand side, I actually have product rule. So I have this blue function, and then I have this red function. So I need to differentiate the blue function first, which is going to give me 2x, and then I still have the e to the y plus, keep the blue function, and then we're going to differentiate the red, which is going to be e to the y. Make sure you tag it every time we differentiate with respect to y. So now I'm here. What I want to do is I want to be able to collect all my dy dx's. We're going to do a little bit of algebra here. I needed to first distribute on the left-hand side. So that's going to give me negative sine x plus y minus dy dx times sine x plus y. And I'm just going to rewrite the second side because nothing changed here. Now I'm going to move all of my non-dy dx terms to the right, all my dy dx terms to the left. So I am going to keep this negative dy over dx, sine of x plus y. On the left, I'm going to actually subtract out this x squared e to the y dy dx. And then I'm going to add over that sine, so I'm going to get sine of x plus y plus 2x e to the y. Now I have my dy dx on one side. I'm just going to just take out a GCF of that dy dx. Don't ever take out anything more than that. We can always reduce our ratios at a later time. And then I'm going to rewrite the right side. And then all we're going to do now is we're going to divide both sides by that negative sign term. So my final answer, and I'll write it right down here, this final answer of dy dx, so when I divide both sides by that term that's next to dy dx, is going to be sine of x plus y plus 2x e to the y all over negative sine x plus y minus x squared e to the y. We cannot cancel any individual terms out. We can only cancel out factors, so don't even think about canceling out the e to the y. Don't even think about canceling out any of the signs. There's no factors. We cannot cancel out just the terms. So we're going to be able to leave this answer as is. And actually, there is a trick to do a problem like this so much faster than what this is. We do teach you this just foundationally so you understand when we move on. But there is a trick to do implicit differentiation a lot faster. And it's probably, I think, a little bit easier too. And if you want to see that, you're going to have to comment below. If I get enough comments, I'll make a video on how to do this a little bit more faster and more efficient. You can always check your work that way too. Okay, now getting to our last problem here, we're going to find the second derivative. So finding the second derivative for implicit is just find the first derivative, then differentiate from there. And we're going to in terms of x and y, and I'll even show you a trick afterwards too about what this could look like in multiple choice. So we're going to go ahead and differentiate this across here. So the derivative of 2x squared is just going to be 4x, and then minus derivative of 6y squared is going to be 12y, tag it, dy dx equals 0. Derivative of 8 is 0. Let's go ahead and make that dy dx all by itself. And actually, I'm going to do that real quick right now. I'm not going to bother with all these semantics of subtracting the 4x and dividing everything over. I'm going to end up with x over 3y. Okay, so that is what dy over dx is equal to. And then once I'm here, I can now take the second derivative. So that's going to involve quotient rule. So d squared y over dx squared is equal to low d high minus high d low. So the low is 3y, derivative of the top is just 1 minus high, and then the derivative of 3y is 3 times dy dx all over the bottom all squared. So I want this in terms of x and y. I'm not done yet. The only thing I need to do is just substitute out the dy dx, and we're going to get a fantastic, really final answer of minus, I'm going to put the 3x like that, times, substitute out that dy dx for x over 3y, all over, really that's going to be 9y squared on the bottom. Okay, now this answer is totally correct. If this is multiple choice though, I can totally see a teacher trying to trick you up a little bit because there is some tricks we can do here. First off, we have a fraction and a fraction. In case you want to simplify any further, in order to simplify this, the easiest way to get rid of a fraction and a fraction is to multiply by whatever that fraction is. Every single term gets this. Okay, so when I do that, I'm going to end up with 9y squared minus 3x squared all over 27y cubed. All right. Everything here is correct. Now, I will say that I can make this look a little bit like this right here. Because if you notice right here, our x term in our original equation is a factor of 1/3 of the y. So really, I can rewrite this equation as 2 times x squared minus 3y squared is equal to 8. And so x squared minus 3y squared is equal to 4. And I can actually rewrite this equation right down here. So coming back down to my derivative, I can actually take out a factor of -3. And if I do that, I'm going to end up with x squared minus 3y squared all over 27y cubed. When I do that, I can actually replace this with a 4. So I'm going to end up with -12 over 27y cubed. Running out of room, I'm going to go ahead and just throw this final answer right up in front right there. We can actually divide all those terms by 3, and we're going to end up with a -4 on top all over 9y cubed. Do not forget to like and subscribe if you want to see more videos like this. And that's it.